To fully understand this video, you should be familiar with the concept of reinforcement learning and have a basic understanding of Markov decision processes, or MDP. Check the links in the description for videos that cover these topics. So, you want to know how the Bellman equation came to be. Let's start with some state, S0, that has three available actions, A1, A2, A3. An agent that takes one of these actions at S0 will transition to one of the states S1 through S5, each with a certain probability. For instance, if the policy at state S0 determines that there is a 0.6 probability of taking action A1, this action might lead to state S1 with 0.7 probability and to state S2 with 0.3 probability. On the other hand, action A2 might have 0.3 probability of being selected, and it may lead to states S2, S3, and S4 with probabilities 0.2, 0.3, and 0.5, respectively, and so on. It is also important to note that the reward received after reaching a certain state may not be fixed. It might vary each time that same state is reached. This means the reward is non-deterministic, and this variability must be taken into account as well. For example, to avoid cluttering the graph, let's zoom in on state S0, action A1, and the resulting state S. If the agent at S0 takes action A1, the resulting state S1 will be associated with a probabilistic reward. The probability of reaching S1 and receiving reward R1 is 0.5. The probability of reaching S1 and receiving reward R1' is 0.2. The probability of reaching S1 and receiving reward R1" is 0.3. Now, back to the full graph. We assign rewards upon entering each state. The value of S0 can be computed using a probability tree diagram. We multiply the probabilities and corresponding values along each branch and then sum all branches to get the total expected value. For example, one branch is S0, A1, S1, so we multiply 0.6 times 0.7 times R1 plus gamma V of S1. Another branch, S0, A1, S2, its value will be 0.6 times 0.3 times R2 plus gamma times V of S2. Then S0, A2, S2. Its value will be 0.3 times 0.2 times R2' plus gamma times V of S2. And the same process continues for branches like S0, A2, S3, etc. At the end, we sum all these branches to compute the total value of S0. Notice how easy it is to understand the concept and perform computations when using tree-like simulation. Let's write it more formally. The value of S0 is the probability pi of taking action A1 times the probability of reaching S1 and getting reward R1 times the term R1 plus gamma times value of S1. We add to that he probability pi of taking action A1 times the probability of reaching S2 and getting reward R2 times the term R2 plus gamma times value of S2, and so on, until the last action and the last state. We are still far from the final form of the Bellman equation. The aim is to write it in a compact format. For this reason, we will rely on a mathematical trick. Let's add to each action the probability of reaching every other state. Meaning, for action A1, we include the expressions that lead to all the states. There's no harm in doing that because we know that action A1 does not reach states S3, S4, S5, thus their probabilities are 0. So the equation is still the same, but with a bunch of other expressions that amount to 0. We perform the same for actions A2 and A3. Now that we have this new settings, we can factor out the action probabilities. So we get each action probability pi times the sum of the rest. Since the second part of each factor is a sum of probabilities over all states and all rewards, we can rewrite it in a compact form by introducing sigma. Thus the equation becomes more compact. Notice that we are summing over all action probabilities pi. So we can compact even more by introducing sigma that will sum all pi over all the available actions. It is like coding for each statement. In this video, We walked step by step through the derivation of the Bellman equation. The goal was to not just present the equation, but to help you understand where it comes from and why it's so fundamental in decision-making under uncertainty. If you followed along, you now have a solid foundation to dive deeper into reinforcement learning topics like dynamic programming, policy iteration, and Q-learning, all of which rely on this core idea. Thanks for watching, and if this helped, consider liking, subscribing, or checking out the next video in the series.